Here. What? Oh, thank you. All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for the students, this class, and just ask you to bless our work today. We thank you for the break, which is upcoming, Lord. In your name I pray, Lord Jesus. Amen. Okay, so you're just talking about, is there something in this class that's not a vector space? Like, well, yeah, plenty of things. But a lot of times I don't talk about those because they're kind of beyond the course, because the structure that's necessary is, well, in the next course, you know, like, for example, this thing, first thing come to mind for me is like GLN. We'll keep it real in here, but this is, you know, A in Rn by n, such that, you know, determinant of A is not equal to 0, if you like. Or you could talk about SLN, which is the set of matrices such that the determinant is 1, right? In fact, also this one, ON, A transpose A equals to I, right? This is actually equal to the union of SON and what you might call minus SON. So here we got determinant 1, and over here determinant minus 1. Oh, no, that's on purpose. This is ON. So if you take an element in ON, you've got the determinant of A transpose A is equal to the determinant of I, right? So that gives us the determinant of A transpose, determinant of A equals to 1, which gives us the determinant of A squared is equal to 1. So the determinant of A is plus or minus 1. So in the orthogonal matrices, there's two kinds of matrices. There's the ones with determinant 1, and there's the ones with determinant minus 1. The ones with determinant 1, we understand, are rotations. The ones with determinant minus 1 are reflections. And so like two of your problems in mission 6, like problems 87 and 88, are really about understanding the structure of rotations in 3 dimensions, you know. And in class, we've more or less talked about the structure of rotations in the plane. And if you read ahead in the book into a section I didn't cover, he actually covers what's the structure of ON in terms of rotations on Rn. And it turns out there's more to say there. But basically, it just devolves into a question of multiple rotations about multiple planes, something like that. But none of these are vector spaces. Not a one of these is a vector space, because if you take the difference of any two of these with itself, you get the 0 matrix, which is not in there. 0 is not in there. It's not a vector space. These are, in fact, all groups. They're groups. A group is a set with an operation which is associative and closed under inversion, right? And that's what you study in Math 421, which is, you know, one of the things that this course is supposed to prepare you for. So, okay, so anyway, that's that. Moving on here. I wanted to talk about the musical morphisms, of course. But first I need to talk about this theorem here, which is theorem, this is Sylvester's law of inertia. And so here's the theorem. Let V, comma G be a real geometry. all right, there exists a basis beta for which the matrix of little g, which we call big G, is equal to diagonal matrix with -1 repeated a few times and 1 then repeated a few times, possibly. Of course, it could be that it's all -1. It could be that it's all 1, okay? But you can choose a basis that puts the form of the matrix of the metric into just a diagonal form with pluses and minuses and 1s. And there's p copies of these, q copies of those. Like that. And the more complete statement of the theorem is that the p and the q are what's the word? They're characteristic of the metric. A little fuzzy here. Maybe it's like the difference of p minus q is an invariant up to a sign or something. I feel like, no, I think the number of p and the number of q is fixed for a given metric. So here's the proof. Let gamma be basis for v, right? And let's let G bar be the matrix of G with respect to gamma, all right? We can apply the real spectral theorem to find an orthonormal. In fact, all right, so let me be a little bit, this is not very good. My bad. So let's see here. Let gamma be the basis for V. Insert this phrase here, selected by real spectral theorem. Why can I do that? Notice that we're assuming G transpose is equal to G, right? So it's a real symmetric matrix. It's self-adjoint. Therefore, there is an orthonormal basis. I'm going to call that orthonormal basis gamma. Okay? There's a now, I guess technically speaking, to be fussy, I say there's an orthonormal basis. I guess fine. I mean, to be fussy, let me stop. So G bar is the basis, the orthonormal basis, and we have eigenvectors x1, x2, xn are eigenvectors, right? All right, so here's my problem. Is like I say it's an orthonormal basis with respect to what? I can't let it go. I'm sorry, guys. I need to talk about this. What do we mean orthonormal basis here? So let me just beg your indulgence. Remember we described that we could take any finite dimensional vector space and create an inner product, right? So I can do that. I'm not talking about I'm not assuming G is an inner product. What I'm saying is that I can pair V with H such that gamma is, orthonormal. right? And like the formula is just h of vi, vj is Kronecker delta ij, right? I can define, pick a basis, pick any basis you like for the vector space, right? Pick any basis you like for the vector space. I can construct the inner product H by extending that formula bilinearly, all right? So it's an inner product space. And then the thing is, with respect to that inner product space, I have a bilinear form G, little g, and it's a symmetric bilinear form, which means it's got a symmetric matrix. So I've got a symmetric matrix, and I can find an H orthonormal basis, right? I can find an H orthonormal basis by the real spectral theorem formed by orthonormal eigenvectors of chi. So this is all how it all goes together. Okay? And so that means then that, of course, we have G times the coordinate vector of x sub I is equal to, lambda I coordinate vector of xi. I say eigenvectors of G. I don't know what that means. Hold on a second here. What am I talking about? I mean, eigenvectors of G. That's just nonsense, isn't it? Right? Is G a linear transformation? I can't say this. This is just crazy. Eigenvectors of what? Eigenvectors of...
Capital G?
It's capital G bar, yeah. G bar. So they're actually, so okay, fine. That means that these are actually column vectors, right? I did say sketch in the notes, right? So I'm trying to make it slightly less sketchy. All right, so far so good, I think. And then the thing is, we can arrange, so notice the determinant of G bar is what? It's not equal to 0, right? Because we assume it's symmetric, which means it's non-degenerate, but we also know something about the determinant, which is what? It's the product of the eigenvalues, right? And no need for complexification or anything fancy here. This is the symmetric matrix. The eigenvalues are all real, right? So these are all non-zero then. Which means that every eigenvalue is either positive or negative. So without loss of generality, arrange them so that you've got lambda 1, lambda 2, all the way out to lambda p less than 0, and lambda, p plus 1, lambda p plus q greater than 0. And here I'm assuming that p plus q is equal to the dimension of the space we're working on. All right? So with respect to this choice of basis, we have the matrix of G looks like what? Well, excuse me, the matrix of rats. G bar times what? Times, gamma. How's it go? Gamma transpose gamma, like this, right? That's equal to what? It's equal to, lambda 1, lambda p, and then lambda p plus 1, lambda p plus q, right? So we want to make a new basis, which makes this just minus ones and ones. What do I do? You guys can figure it out. How should I change the basis that we have to change these eigenvalues? I want my new basis to do like, let's say gamma tilde transpose G bar gamma tilde to be equal to what? Minus 1, minus 1 p fold times, and then 1 q fold times, right? What should I do? Just it's pretty easy to figure it out, right? Y sub I is equal to what? X sub I divided by the square root of the absolute value of lambda I. And if I do that, I get this. So like going back to G, so I got like G of yi, yj is equal to G of xi over the square root of the absolute value of lambda I, comma, xj over the square root of the absolute value of lambda j. Use the, pull out, I've got 1 over the square root of the absolute value of lambda I, square root of the absolute value of lambda j, right? And then I've got G of xi, xj, which is equal to, lambda I. When you work this out, this gives us lambda I Kronecker delta ij divided by, the square root of the absolute value of lambda I, square root of the absolute value of lambda j, which is equal to, plus or minus Kronecker delta ij, where the plus or minus is determined by whether or not I and j are both in the first p values, or I and j are both in the I is equal to j, and it's one of the last q values. Because we've got absolute value down there, and that absolute value is either the plus or minus the eigenvalue. Like this simplifies to the square root of the absolute value of lambda I squared if I is equal to j, right? Which is just the absolute value of lambda I, right? Which is plus or minus lambda I, which is why we get that. Yeah.
Should that be lambda I on j?
Where did I do it? I don't think so. You could be right, though. Let me think. So, well, everything I'm doing is a little bit is a little bit suspect, right? I'm sorry. Like, I can't even do what I'm doing, right? Because I can't put, these are column vectors. I'm putting column vectors into the abstract bilinear mapping. That's not right. So, like, I need to, say something like, well, anyway. This isn't quite right. I should do something like, well, yeah, well, I need to, I'm just going to put some tildes on here, if you don't mind, and understand that to be fussy, I need to track back through the coordinate maps to get the eigenvectors in the vector space. But to make this explicit, I'd have to get into the business of the coordinate map that I got here from, which was the gamma coordinate map, I think. So like, what I'm suggesting is not much. I mean, just I think x sub I with respect to, it was gamma, right? Yeah, the gamma this is equal to x. Good grief, x tilde is this. That's all I'm saying. So, and likewise for the y tilde. And what I know is that g xi is equal to lambda xi, and I also know that g of x tilde y tilde is equal to the coordinate vector of x tilde with respect to gamma times the g bar times the coordinate vector of y tilde with respect to gamma.
Could there get transpose in there?
Yes. Thank you. And for that reason, there's only one lambda. See, because when I put the g of x tilde, I'm going to just do the x's. X tilde I, y tilde I, because the y's have got all this mess down here, okay? If I could just write what I say, it would be wonderful. So x tilde I, x tilde j, bad people. Let's see here. So, this is, so I get xi transpose g bar xj, which is xi transpose lambda j xj. But remember, these are orthonormal. Anyway, so that's why I have that. All right. So anyway, this is Sylvester's theorem. And what Sylvester's theorem in a nutshell says is really that like the Euclidean metric and the Minkowski metric that we already looked at, they're not so unusual. In fact, they're very typical. And so you might wonder that like, is there some kind of, like what do metrics look like? And the answer is up to a change of coordinates, they look like what we already looked at, like either Euclidean space or Minkowski space, but you see there's other variations on this theme, right? Because you could have a different number of pluses and minuses, Like you could have, like here's I don't want to fix a notation in here, but a notation you might consider would be something like this. You could look at something like 023. And that would be maybe like A in R5 by 5, such that A transpose eta 23, A is equal to eta 23. What's eta 23? Well, this is example what? Example 1? Example 1. Here I mean eta 23 is something like, I don't know, maybe you got -1, -1, and then 1, 1, 1. This would be some sort of 5-dimensional time space. It would have 2 time dimensions, 2 temporal dimensions, and 3 spatial dimensions. Well, I put the I think of the minuses as time. But you're right. You could also think of it as you could in fact you could indeedly doodly, you could flip the script and look at ds squared, which was something more like dx squared minus dy squared plus dt1 squared plus dt2 squared. I think we've left the notation of this course behind. My apologies. Sorry, my advanced calculus is showing. Let me erase that. Parentheses there, parenthetical comment. There you go. Anyway, so let us get back to the musical morphisms before I regret my life, because I seem to have a problem getting to them. I really do want to talk about them. So let's do it. So what is the musical morphism? So definition, beta of x upper I is equal to x lower I, and sharp of alpha lower I is equal to alpha upper I, where in particular this is defined to be the sum j equals 1 to n of x upper I, g lower ij, and this is equal to the sum, say j equals 1 to n of alpha lower I, g upper, oh man, that was alpha lower j. What did I just do? Oh, just a second, guys, I did it wrong. Don't write this down yet. Alpha lower j, g, oh good grief. It doesn't matter which, let me stick with my notes. So alpha I, goodness gracious. There's a typo in the notes here. That was supposed to be an alpha sub j in the notes right here. Alpha sub j, g upper ij. It doesn't really matter the order of the indices because remember G is symmetric, and it turns out that the inverse of a symmetric matrix is also symmetric. Yay. But this was supposed to be a J. Again, this, we could just as well write this. I'm not being dogmatic about it, okay? There's a typo in my notes, so it's really unclear in this regard. I'm sorry about that, but it is what it is. But because G is symmetric, we can do this, all right? Let me remind again, what are the G's? So like here, we're working in a metric geometry, right? So like we have a G orthonormal basis. This is all being done with respect to a G orthonormal basis, right? So here we have x, just to recap here, is equal to I equals 1 to n of x upper I, v lower I, where, you know, just to be clear, beta, v1, vn is G orthonormal. I can't say orthonormal, G orthogonal basis. Why can't I say normal? We talked about that last time for too long. Let me not get into it again. All right. Alpha, on the other hand, is a dual vector, and it is equal to the sum I equals 1 to n of like alpha I, v upper I, right? Where beta dual, remember, is the v upper, v with the upper indices. And how are they related? Well, whoa. V upper I acting on v lower j is Kronecker delta ij, right? We also, let me just refresh your memory about some other things. Like, do you remember what the deal was? We had some previous lemmas we worked out, right? For one thing, we could write x is equal to the sum I equals 1 to n of like v upper I acting on x times v lower I. And we could also write alpha as equal to the sum I equals 1 to n of alpha acting on v lower I times v upper I. In other words, simply put, v upper I acting on x is xi, and alpha sub I is exactly alpha acting on v lower I. So to get the components of a dual vector, or to get the components of a vector, we simply can operate on the corresponding, you know, basis element of the other object. So either, well, but this is how to, I mean, this is how to select components in terms of the dual basis or the basis, yeah? Let me give a example if I've got time. I do have time, woohoo!
What is x sub I?
What is what?
X sub I.
that is the covariant component of X. It's beta of Xi. Beta. So these are the covariant
Oh, okay, so that's not
component
something we already did.
of X. Whereas this, just X by itself, is the so-called contravariant component of X. Now, I mean, to be fussy, X sub I is not really a component of X. It's a component of a corresponding dual vector. Let me finish this story here. Jeez. So, example 2. Let me actually look at a specific example here. I'll make it relatively easy so we can understand it. So let's suppose we have like V equals to, let's say, R3, and the matrix of G is 1, 2, 3. All right? So this is, like explicitly, we have, G of x comma y is equal to x1, y1 plus, 2, x2, y2 plus 3, x3, y3. There you go. That's the formula for this. Oh, let me make it exciting. This is an inner product. It's too nice. Let's slap a minus on the first one. There we go. Exciting. So, all right. If that's, so this is, I hope you can agree with me that's the matrix for this, right? Okay, so what's the inverse to G? Minus 1, 1/2, 1/3, right? So G, so these are the components of G upper ij. So let's look at a specific example like, well, you guys, give me whatever vector you'd like. We want. 0, 1, 3 million. I'm going to take that and replace it with a 7, 8, 9. So, thank you though. So what are the contravariant components of X? X1 is 7. X2 is 8. I don't know what they're doing today, but it's something. X3 is 9. All right? So it's probably good for me to extend the definition of the flat map because the proper definition is given. Let me give it right now, and then we'll use it, okay? So, like, flat of X is equal to the sum I equals 1 to n of flat, flat, I'm not good at making flats, flat x upper I times v upper I. Right? Explicitly, that's the sum I comma j equals 1 to n of g I j x upper j v upper I. And similarly, the sharp of alpha is defined to be the sum I equals 1 to n of sharp of alpha sub I comma j. Oh, that's fine. Alpha I v lower I, which is equal to the sum over I and j of G upper I j alpha sub j v lower I. This is an element of V dual. This is an element of V. So like, just to stick a fork in it here, flat is a mapping that goes from my vector space to the dual space, and sharp is a mapping that goes from the dual space back to the vector space. And my claim is that both of these maps are isomorphisms. But more than that, they're isomorphisms which naturally play together with the metric involved. All right, so now that I've finished giving you the definitions, let's continue on with our example. What is like, so to be clear, this x was what? This x was also equal to like 7e1 plus 8e2 plus 9e3, right? So here v1 is e1, v2 is e2, v3 is e3, lower indices, the vectors. What would the flat of x be here? So if I follow my definition there, sum ij equals 1 to 3 of g upper ij, right? Of, oh my bad, I can't even follow my own definition. This one, not that one. G lower ij, let's try this again. G lower ij of x upper j, and v upper I is what here? It is e upper I, right? The dual basis for Rn, R3. Okay? And in this particular context, Gij is what? It's 0 unless I is equal to j. And then if I is equal to j, it's either -1, 2, or 3, depending on whether you're in the first, the second, or the third case. And so what this works out to, of course, is just g11 x1 e1 plus g22 x2 e2 plus g33 x3 e3, which is what? Minus, what was x1? 7. So minus 7 e1 plus what?
16 e2.
2 was just
16 e2.
16. That's not a 2 times 8. Where'd you get the 8?
x2.
That's not a square. That's a label.
So x is 7, 8, 9. So
Oh.
x.
Oh, I'm sorry. I'm a dummy. 7, 8, yeah, 2 times. You're right.
So is G lower ij the components
So
of
6.
the matrix?
Just a second. 16 e2, right? What'd you say? Sorry.
Is G lower ij the components of the G matrix?
Yes. That is our definition. And then, so this is 9 times 3, which is what? 27 e3. So that is the dual vector, which corresponds to my x. What happens if we take, so if we call this thing alpha for a second, right? What is going to happen if we calculate the sharp of that alpha? What do you think? So notice here we've got alpha 1 is -7, alpha 2 is 16, alpha 3 is 27. Right? Those are the components of this one. And so this is Uh, I'll write it symbolically for a second here. It is, oh goodness gracious, G11 alpha 1 V1 plus G22 upper 22 alpha 2 V2 plus G upper 3 3 alpha 3 V3, right? And explicitly, that's, what is G upper 1? Well, G upper 1 is minus, so we get a minus, and my alpha 1 was what? Minus, so I get minus a minus 7, that's E1, right? G22 is 1/2, right? So I get plus what? 1/2 of 8 E2? Not 8, alpha 2 was what? 16, right? And then plus 1/3 of 27 E3. What do I get? We get back X, right? Get back X again. So what we've just demonstrated for my example is that the flat and the sharp are inverse. They're inverse maps, right? Yeah.
Just to make sure I'm understanding it right. So you have the example 2 line, and the line under that is G of X, Y minus example 1 y. Is that a scalar?
Which way? Where?
At the top of the example. Example 2, it's G of X, Y equals minus example 1 y.
Yes, this is a scalar because G is a metric. Remember, a metric is a mapping from V cross V into the reals.
But the X and Y's are
Components of the vector X and the vector Y. X1, X upper 1, X upper 2, X upper 3, these are numbers. Specifically 7, 8, and 9.
the components in the dual space.
What's that?
They're the components in the dual space.
No, they're the components of the vector. Now you can get them from the dual space. It is true that like X1 is also equal to E upper 1 acting on X. That is true. This is E upper 2 acting on X. This is E upper 3 acting on X. These things are also true. We can understand components in terms of the dual basis acting on the vector, because remember, the dual basis is nothing more than the component functions of the coordinate map. So there's a connection there. But what I hopefully have just demonstrated is that we could look at V here. We can look at V dual over here, right? And the flat map takes me like that, and the sharp map takes me like this, right? And we could do this calculation in general, rather than just for my example, and get the same result. Maybe it would be a good calculation to do. That's a homework problem? That might be that does feel like a homework problem. You think it is though? Yeah. I better not do that then. Violet would be disappointed if she didn't have the chance to discover it for herself. No? Too tired to care? Okay, very good. So let's see here. It's easy to get lost in my formulas. These formulas are motivated in part from physics. So like in physics, the notation is sometimes used something like this. So here's how it goes in physics. You have something like x. In physics, they use mu for an index. So something like this, x mu, x mu. If the index is repeated, that means it's summed over. So this is actually just a notation for like the sum mu equals 0 to 3 of x mu, x mu, right? I'll put some quotes around this because we don't do this. This is physicists, you know. And what this means, though, is actually, I mean, there's two different ways to look at it. You, on the one hand, could look at it like this. Could look at it like that. But you could also look at it like this. So using the metric, using the inverse metric, all right? And if you look in the notes, I do prove that I do some calculations which studies the interrelation of these two things, you know. But the larger point here is that the coordinate change, if we change coordinates, right, it turns out that the x upper mu and the x lower nu, these transform inversely, like the one changes one way and the other changes the other way. And because they change in opposite, but they change in inverse ways, the net result is that that's an invariant. No matter what coordinate system I pick, that's a constant. So this is why physicists are interested in this, is because it gives them a way of calculating things that are invariant with respect to their change of coordinates. But you see, once you have this, we can change tensor types, you know. So let's see here if I can, one other thing. So let's see here. We are trying to, basically the fundamental question is, how do you take a vector x and convert it to a corresponding, dual vector? Let's say x sub alpha sub x in v dual, right? Right. How do we accomplish that? Like, how do we get an isomorphism of a vector space in its dual space? So when we first came across this question in here, I gave you an argument, but it was based on like picking a basis, right? We picked a basis and then we used the dual basis. Basically, that gave us the isomorphism. Essentially, that is the isomorphism. Map the basis to the dual basis. That's extend that linearly. That gives us the isomorphism. But there's a basis independent way we can do it in the presence of a metric, right? In metric geometry, we simply do this. Alpha x of y is equal to what? I can give you a formula which is linear in y and its output is a scalar without any choice of basis here. What is the formula? We're in a metric geometry context, right? VG is a metric geometry. What do I put here to get a number? Oh, no need for adjoint here. The only thing we have to work with is G, right? G of what? What we do is we do G of what?
X, Y.
Uh-huh. Yeah. Check it out. This is linear in y, right? And it's in fact a unique, it's an invertible map actually. What I'm saying is that the mapping, so all I'm really saying is you take the map x and you map it to, and this is the notation you'll see sometimes, G comma with like a slot. That's the isomorphism. You're inputting a vector and your output is a dual vector because this is naturally interpreted as a mapping from the vector space to the rails. No choice of basis was made here. So my use of basis in the construction of the flat and the sharp maps is illusory. If you look at the calculation I do in the notes, I prove that you're right. This is flat x acting on y, right? That's true. You're right. That is what that is. Who said it? Okay, Joshua. Okay. You're right. But I wanted to take a second to say, by the way, my hideous use of coordinates is unnecessary. Like, we can write down the isomorphism just using the metric alone. So like, if I'm given a tensor, like a mapping from, say, V cross V to the reals, and I want to induce a new tensor, say t tilde, that goes from, say, v dual cross v to the reals, well, then I can just do something like t tilde is equal to, t composed with what? I just, like basically do the flat map and, with the identity. And so like this mapping will take v to v, and it'll take v to v dual, and so like I'm converting, or wait a minute, the other way around. Yeah, so I think this should go from v cross v to v dual cross v. My bad. Wait. I'm sorry, guys. Yeah, that's what I wanted. I'm sorry. Yeah. What did I want? Yeah, that's what I was trying to. Thank you. So maybe I've got the wrong map, because I want to convert that to. I need the sharp, right? So sharp converts v dual to v, and then of course this I already am given. So this is the t map. So I can strategically use the sharp and the dual map to convert inputs from vectors to dual vectors and vice versa. So if I'm having a tensor, like a multilinear map on a particular copy of like vector spaces in its dual, I can use, in the presence of a metric geometry, the sharp and the flat maps to convert it to other kinds of tensors. Physicists use this idea extensively in writing equations. But anyway, I'm sure I'm out of time. But I think I've done justice to it, or injustice. Anyway, a good amount of both. Have a good break.